For most of human history, we have looked at Mars and seen one thing: a small, red, frozen world. Dead, quiet, dry. A planet that, for as long as anyone has been watching, has looked exactly the same. But for decades, scientists wondered, did Mars always look like this? The answer, it turned out, was hiding in the dust, in one specific kind of rock, a rock that on Earth almost never forms unless water is present. And on a January day in 2004, a small rover bounced down onto the Martian surface, and within days found that exact rock everywhere it looked. Tiny iron-rich beads scattered across the ground like seeds. They called them blueberries. And they were the smoking gun. Billions of years ago, Mars had been a completely different planet. Modern Mars is brutal. The average surface temperature hovers around -63 degrees Celsius, close to -81 Fahrenheit. The atmosphere is less than 1% the pressure of Earth's. There is almost no liquid water anywhere on the surface, and what little water exists is locked into the polar ice caps and the subsurface. If you stood on Mars without a suit, you would not last seconds. For most of human observation, that was the assumption, that this had always been Mars, a cold, thin, lifeless world. But starting in the late 20th century, the picture began to crack. Channels carved across the surface looked suspiciously like ancient riverbeds. Vast, dry basins resembled lake floors. Sediment patterns matched what flowing water leaves behind on Earth. It was suggestive, but never definitive. Wind, ice, lava, even meteor impacts could carve similar patterns. To be certain Mars had once had liquid water, we needed something else. We needed a chemical fingerprint, and in the year 2000, one finally arrived. In 1996, NASA launched a spacecraft called Mars Global Surveyor. Among its instruments was a thermal emission spectrometer, a device capable of identifying minerals on the Martian surface from orbit based on how they radiate heat. In 2000, that instrument detected something extraordinary: a vast deposit of gray crystalline hematite in a flat region called Meridiani Planum. Hematite is an iron oxide. There are several forms of it, but the gray crystalline kind that the spectrometer had found on Earth commonly forms in environments involving liquid water. It was one of the strongest hints yet that Mars had once hosted persistent liquid water. To confirm what it meant, we had to actually go there, and 4 years later we did. On January 25th, 2004, a small rover the size of a golf cart, wrapped in an enormous cluster of inflated airbags, bounced down onto Meridiani Planum at over 100 kilometers per hour. It bounced more than 24 times across the surface before finally rolling to a stop. Its name was Opportunity. Its mission was supposed to last 90 days. It would, in the end, last nearly 15 years, only finally going silent in June of 2018. After a planet-wide dust storm blocked the sunlight from reaching its solar panels. By the end of its mission, Opportunity had crossed roughly 45 kilometers of Martian terrain, the longest distance any vehicle has ever traveled on another world. But the most important discovery came in the very first days. Within days of landing, Opportunity began sending back close-up images of the rock around it, and scattered across the surface, embedded in the soil and the eroded outcrops, were thousands upon thousands of tiny, almost perfectly round spheres. A few millimeters across each, dark, smooth, surprisingly uniform. Scientists nicknamed them Blueberries. And when the rover analyzed them, the answer came back almost immediately. They were made of hematite. These were not random rocks. They were concretions. Formations that grow when mineral-rich water percolates through stone, slowly depositing material in concentric layers. On Earth, identical formations are found in places like southern Utah, where groundwater has been moving through sandstone for millions of years. It wasn't a hint anymore. It was a direct physical confirmation. Mars had once had abundant groundwater. Lots of it. For long periods, long enough to build, grain by grain, vast numbers of little iron-rich beads. This is where the story becomes something else. Because if Mars once had standing water, then Mars once had something close to a climate. In the deep past, around 3 to 4 billion years ago, the planet looked very different. The atmosphere was thicker, temperatures in places warmer. There were probably lakes, probably rivers, possibly shallow seas. There may have been weather, rain, maybe even snow, and there may have been the chemical conditions for life. We do not yet know if life ever actually emerged on Mars. That is one of the great open questions of planetary science. But the opportunity for it, the chemistry, the water, the warmth, was there. For some unknown stretch of time, Mars was not a dead, red rock. It was a world, and then it ended. Not in a single event, not in fire or impact, but slowly, over hundreds of millions of years, more than 4 billion years ago, Mars largely lost its global magnetic field. The internal dynamo that had been generating it slowed and stopped, possibly because the planet's small core cooled too quickly. Without that protective field, the solar wind, the constant stream of charged particles from the sun, began stripping away the Martian atmosphere, one molecule at a time. The atmosphere thinned, pressure dropped. The greenhouse effect that had kept Mars warm faded with it. Temperatures plunged. Liquid water boiled off into thin air, escaped into space, or froze beneath the ground. Over the next hundreds of millions of years, the wet, warmer Mars slowly turned into the cold, dry planet we see today. Those small dark spheres are among the most compelling remnants of that lost world. Tiny mineral signatures of a world that ended. But the story didn't end with Opportunity. Opportunity's discovery was just the beginning. In 2012, NASA's Curiosity rover landed inside Gale Crater, a former lake bed where the rocks have preserved an entire chemical history of ancient Martian water. Curiosity has been climbing the layers ever since, reading the Martian past out of the stone. In 2021, the Perseverance rover touched down at Jezero Crater, the site of an ancient river delta, where flowing water once carried sediment into a standing body of water. It is now collecting and storing samples that NASA hopes to eventually return to Earth for direct laboratory analysis. And recent studies even suggest that, deep beneath Mars's surface, substantial reservoirs of water may still exist today. Buried, hidden, and perhaps in some places still liquid. Mars may not be as completely dead as we used to think, but the warm, wet world is gone. When we land a rover on the moon, or fly past a giant moon of Jupiter, we are studying those worlds for what they are. But when we send a rover to Mars, we are increasingly studying it for what it was. A planet that, somewhere in the very deep past, had water on its surface, had a climate, had, possibly, the conditions for life, and then lost all of it. The proof is scattered across the soil of Meridiani Planum, in tiny iron beads barely the size of peas. A whole world's history in a handful of blueberries.